super sorry about the delay, but so I cut short a little bit about the review, but we should be able to do it on time. But very terribly sorry about that. So the goal today is to almost finish this part, probably except a few last few slides we can't finish. But that means that the assignment will only be released next Wednesday, because next Wednesday we finish. Okay. So because of my problem, we cut short about the review and go immediately to what we want to do. So just still, I do a very quick reminder. What we're doing is we start from the probability that I hope it's recording. Maybe. Hello, that's fine. So it's the classical one is depending on the idea that experiment can be repeated. So it has to be something that potentially can work out many times and doesn't change a lot. So it's like the standard gambling would work, but when you have things that can't repeat, then it's hard to do the idea that you repeat the experiment many times and look at how many outcomes that favorable to event and over the total number of experiment. And for example, you want to say business decision in the future that rely on our past data or our knowledge of our business, that doesn't work very well. The reason is it can't be repeated, right? The business today is different from tomorrow or yesterday, right? So things are different. So we have to use a more complicated approach, and that means that we have to rely on a new framework which doesn't require on things can be repeated, right? And the example we like this is like rolling a die, and we have to build up the axiomatic work is to look at the probability in three axioms, right? The first axiom is saying that everything is between 0 to 1, and do remind you that between 0 to 1 is non-trivial, because like odd ratio is a measure probability, but it's from 0 to infinity. So 0 to 1 do have some meaning, right? Of course, if you top a ratio, 0 to 1 is natural, but do remind you that 0 to 1 is not something have to be, right? It can be 0 to 2, 0 to 3, but 0 to 1 fit our idea of relative frequency, right? This the standard classical way. And second is the sample space is 1. And this is also non-trivial. It means that we know everything about what we want to study, right? It's something that you have in order to say something in probability, in that sense, you have to know what's going on, at least in theory, what might come out. It can't be outcome that is not in our prior consideration, right? Just like the idea, right? You go to see a magic show, and then the magician pull a rabbit out of the hat. That is something unexpected, right? It's unexpected even in the outcome. So that is not, we can't say properly the probability in that sense. And lastly is the idea that probability sum is sum of the probability of all the parts, right? The whole is sum of the parts, and this is non-trivial. If finite is trivial, but infinite is non-trivial, and infinite is often we use in finance or in other cases. That is something we need to look at. And say, for example, we die, right? Even number would be probability. Get the even number with probably sum of 2, 4, and 6. So this is something very natural. But if the number that infinity or 0 to 100, any real number, that is non-trivial, because you have to cut them many, many small pieces. Adding all infinite pieces need not be equal to the sum. So this is not guaranteed to be whole. So that is a major bite there. But for our purpose, we will not touch on these technical issues. But if you want, you can go to the math department, stat department. The 4,000 classes or master class will go over that, but that is not what we want to do. So just to remind you this example again, because this is very important. I mean, you will overlook it when the first time you read it. First, you can see the sample space is 1 to 6, and because of the axiom 2 is the whole thing is 1, and axiom 3 is saying that because it's mutually exclusive, the outcomes. So probability sum is probably sum of all its parts is 1 up to 6. So up to here is nothing about the real world, right? Nothing about the knowledge there. But on the next point, we say the die is fair. That is our assumption. do remind yourself that we never actually do any experiment there. But by the assumption, we make this assumption. How? Because we know engineering. When we produce a die, if the machine is nicely done, or the die you see engineered perfect, then this is a fair thing, right? Or that's from the data, right? That's also experiment, but it's not repeatable, right? It's not reasonably repeatable, right? Then it still can be done. So our business judgment, that will be the case, is like look at the financial market, right? If you think that what happened in the past is going to be true in the future, that is the data can tell us how to get those P's, right? And that would be the key, right? And the next thing is this free axiom is sufficient to build up everything we want, right? Because we only allow interset or union or interset or complement are the basic operation on the event. So as long as we consider them, then we consider everything there. So that would be the idea. And quickly about complement rule is saying that if the probability event would be equal to 1 minus its complement. So basically just convenient, right? Because we talk about this kind of probability, we may be able to have some data on some outcomes, but not the others, right? So in order to those, this is the idea, right? Because unless we know everything, if we know everything, then we're done. But in the case that we don't, then this is a convenient. And similarly, this the case with addition rule, right? The probability of OR is equal to the sum minus the intercept. So this is the case where the XM3 doesn't hold directly, right? XM3 was said if they're mutually exclusive, then we just add them up. But in the case of not mutually exclusive, what can we do? It's just minus intercept. Okay, and that is the example. I'm not going to repeat it. I guess it's fine. And the graphic is like this, right? It's the red circle plus the purple circle. You double count the pink one, so minus the pink one will be equal to the whole total area. And the total probability rule will be the A is equal to A with B and A without B, right? Just directly, it's just like the red circle is the area with the pink one will be this one. That's the first area, and plus this second area, right? So that would be sum of the two parts will be equal to the whole. So we'll use it way often soon when we talk about the thing. Because the odd ratio, I think remind you already. Just this is the way in the past that people talk about probability, because think of the normalizing from 0 to 1 is not very natural. And usually when we talk about things equally likely happen or not, then odd ratio is 1. So that's why, right? If you don't know, odd ratio is 1. So that is a very natural thing to do. This is usually the graph you see. And I talk about in the betting odds that is happening in the casino, right? That would be the inverse of the betting odd will be exactly like the odd ratio, right? And then we can estimate probability of the odds. Okay, so that is very important because we infer probability from the real world market, the casino market, and that's how often happen used in finance industry as well. We of course now everything you go online to the poly market, everything can be bet. So in that sense, if you believe that the betting market online, the poly market is a good one, then this is something we get. Okay, and more or less we kind of stop here, I guess, right? Stop somewhere here. Maybe multiplication rule. So let me remind you this definition of conditional probability. I think I can slow down a little bit. So this idea of conditional probability imply that if I know B has happened, or B is my working hypothesis, what should I do? Okay, here means that the sample space strength from the S to B. Okay, and why you have this equation there? The first thing you can see is, since it's a probability, right? So the maximum must be 1. So I should have probability B in given B should be 1, right? Because I know B has happened, right? So it gives me the sample space, which is now is B, it should be 1. So suppose I have B and intercept B, and that is just still B, right? So that should be 1, right? Because this is B. Then it should be 1. And the first thing, that's why you have to divide it by B. The next thing is why is A intercept B? It's because now you know B has happened. Okay. So only thing that together with B would be meaningful. So that is what you get. Okay. So if you want to see this is why this is true, it's just this example again. Okay. You have a rolling dice. There's an even and large. And you know large has happened. So only the sample space is no longer 1 to 6, but rather is 4 to 6. So even also changed from 2, 4, 6 become 4 and 6. Okay. So that is the reason why it shrinks from even is before is 3 over 6, but now it becomes 2 over 3. It's because of the sample space shrinks. Now the new S is L, and E become 4 and 6. But this is rather complicated. If you every time you do it, you have to shrink the sample space, that your life will be miserable. Okay, so that's why we invent a formula. Actually, you can prove it. This by looking at the formula we have given to you. Okay, and if you look at advanced math textbook, they will tell you how to prove this one, but we don't want to do it, so just we take it as definition. Okay, at a moment, but this is actually can be proved, but we take it as definition. Okay, now the idea is like this, right? Just like the strength from the big thing to the smaller one, and you calculate everything in the smaller sample space. Okay, and you can do it the calculation by look at this one. So here is we are another rule is called the multiplication rule. Is we are arranging the equation that we have just defined. Okay, you multiply both sides by probability B, you cancel out the denominator, or you just move the other side, right? So probability A intercept B will be A given B times B or B given A times A, right? So that would be the idea. Again, this is very useful when you do things one by one or sequentially, and later you will see this is very convenient. We will see this actually build you what we call the base rule from this one. Okay. But before we do that, let's see this example again. I mean, I guess did I cover this one? Right. So this is a very simple idea, right? We have a 3 white ball and 3 black ball, and then we've got to draw 2 balls from that, and then you want to have 2 bad. Okay. And it's the black and black, right? Then you can do black 1 and black 2 given black 1. Okay. First one's black is 3 over 6, right? Which is natural because of 6 balls, and out of which 3 of them are black, right? But the second one you drawn will be, because once you draw the black, only 5 ball left, and 2 of them is black, so it's 2 of 5. So just multiply them, you get what you want. Okay, so this is a very convenient multiplication, and turn out this is this 3 is I would explain in detail because we will need that table. Okay, so you can see from this one, this is step 1, right? Step 1 is 1/2 for each edge. Okay, but do note that when the second time when you draw, do these 2 cases, the orange and the pink are different, right? Because it depends on what you have drawn. Okay, and in that case, when you draw the black and the white are actually exactly opposite, depends on what you have drawn, right? Because in the first case, upper edges, black is less likely because once you draw a black, then you have more white than black. But below you have draw a white one, then black is more than white. Okay. And after these 2 actions, indeed what you left is only 4 possible outcomes, right? You have 2 blacks, black and white, white and black, and white and white. Okay. And how to get this outcome? The tree will tell you that we can apply the multiplication rule. Okay. The end outcome is multiplying along the edge, how you get there. And this multiplication rule indeed apply to a very big tree. So suppose you you continue to do a third draw, so on and so forth, the end probability just multiply all the way up. Okay, so that is something that the multiplication rule I didn't write down in the equation, but you can easily extend this knowledge if I have a big tree there. And the probability of getting 2 black is this one, right? And if I ask a question like, what's the probability that you draw only one black? Okay. In that case, look at this tree. You will add these two edges together, right? Because these cases is you have only one black, right? So it would be 6/10, right? If you ask the question is, what's the probability that at least one is black? Then in that case, you add up these 3 branches, right? Because the first 3 are probability of getting black. Is that clear? Okay. So this is very convenient, right? So basically you would multiply along the edges and then you add up across edges, right? So that is the very convenient way. And then I'll suggest you when you do a complicated problem, this is a very good way to go. Okay. So we will do this again very soon, the Bayes theorem. So keep in mind how you're going to draw this diagram, the tree diagram. So here is the formula, we combine the two. So this we have seen, right? A is A with B and without B. We have seen that before. Okay. Now what is new here is we have this A intercept B decomposed into 2 parts. Okay. B given B, right? Probably B times A given B. Okay. This is the new thing, but this is just multiplication rule, right? And we again apply multiplication again, right? Decompose in 2 parts. Okay. So that is the rule. We will use it very soon. Okay. First line is total probability rule, and second line is multiplication rule. Okay, because it's just you do B first, and then given B was A, right? So let me repeat in word. Probability A. The first line is A is decomposed 2 parts. Is A with B and then without B. The second part is A and A with B will be look at how B is likely, okay, and times given B happen how A is likely. Okay, we do B first and how likely A under B. Okay, same as the next one. Okay, so I guess this is okay. This example to give you the idea what's going on here. So I have a bet A, 4 whites and 1 green. Another bet B is 1 white and 1 green. Okay, and a bet is chosen random, and a ball is drawn random. Okay, I choose the bet first, and I draw a ball. So I close my eye and pick whether A or B. Once I pick A or B, I draw a ball from the bet. Okay, the question is, how likely is a white ball? Okay, okay. So maybe you look at this, looks crazy, right? And it's easier to look at the diagram first. Okay, this is easier, I would say, right? The first round you do is you pick a ball, put a bet, which is A or B. You close your eye, equally likely. Okay, of course, it need not be fully random. Maybe you are more likely to pick A or B, right? Maybe A is looks more attractive, right? Whatever, but make it easier. Okay, A is equally likely. Okay, and once you draw A, then you have a 4 whites and 1 green, right? Then white is more likely because you close your eye and draw the ball, right? It's 4/5, and green is 1/5. And similarly, is 1 white and 1 green, then will be equally likely because same. Okay. Then remember the multiplication rule is you multiply along the edges, you get the end outcome, right? You draw A bet and white ball will be just multiply along. If A bet and green ball will be just multiply along this outcome, right? This go with this one, and multiply this to go this one, right? And remember the question is how likely I draw a white ball. Okay, then it just I have the first edge and the third edge there, add up together is my answer, right? But that is exactly the equation I said. Use the total probability rule and then multiplication rule, right? That is going back to the previous one, right? W is W and A, W and B, right? It's just this edge plus this edge, right? First edge plus the third. And then how you do it, how you get first and third, you go back from here, you go back to the source, multiply along. Right? So just the idea is you need this guy and this guy. Right? White is either whites with A and whites with B. Right? How to get whites with A? You go back white and A, right? Multiply along backwardly. Right? Here, how to get this? B and white, you go back. These two numbers. Is that clear how you get the equation? Okay. But probably in your mind, why am I care about this crazy bad drawing exercise? Right? Or why who is going to pick a ball from a bat and close your eye, pick a bat? Who is going to do that? Why are we doing that? Why we're doing that? I mean, is it something crazy? Some people drawing bad, close your eye? No. If you think the following: stock market. What's A and B? A and B is economy. A is economy is good. B, economy is bad. Okay? And economy good, white is stock price goes up. G is stock price goes down. Same for the bad B, bad economy, right? So let me write that down. This is good economy. This is bad economy, right? Then the stock price goes up. Stock price goes down. Price goes up. Price goes down. So what the question is asking is, how likely the stock price goes up? And how do you analyze this? You analyze this by dividing the situation into two cases. It's hard to give you the probability, but if I tell you, if we divide analysis into two scenarios, good economy, price goes up more likely. Bad economy, maybe equal likely, right? And then you can divide and conquer, right? That's what you do in scenario analysis. Divide your analysis into different scenarios, and in each scenario, you do your analysis, right? And then you analyze how likely each scenario comes out. Not necessarily one half and one half, right? You have your guess on this one, right? Then you can guess what it is, right? And some of you say, oh, okay, this is trivial. But if you actually study option pricing, that's what option pricing is being done, right? This is actually what they call the binomial tree. If you go to option pricing classes, they will tell you that this is each day. So day number one is like this, day number two is like this, then they build this tree very long. And go back from the end day, go back, you can evaluate the call option for European option. So that is what you learn. If you go to the further 3,000 classes, you can actually calculate those. You can calculate probability on each tree, right? And calculate in each event what is the value of the option, and then you can backward calculate how is the value of the option. So this is thing that you actually do when you do the option pricing, or when you predict your stop price, where the stop price is. So something is very naturally done. So it's not there I care about open the bet and which the ball to draw, but it's actually the thing there, right? Or you can think the bank, right? The bank is lending money to a guy. If the business, it depends on whether the company actually has a breakthrough in the technology, right? So maybe he has doing some new technology, you lend the money to that guy, and then if he has some breakthrough, right? And then this will happen. If not, then equal likely he will go, he can do good business and he's bad, right? So on and so forth, right? This is a very natural thing, because you can't analyze the situation once and for all, but you divide them into different scenarios, and this structure, the tree, is very useful. Okay, so I hope I convince you that this is an important question, and this is a very useful thing that actually we do all the time. Is that okay? Now we have the independence, okay? And the independence is a very important concept which we will use for the second half of our course. Okay, what is this? It's saying that if two events are independent, telling us whether one of them has happened or not, has no information about the others. Okay, so the definition is very simple. Say, like you can see here, telling us whether B happened or not has no information, or telling A has no information of B, or the intercept is this one, right? Because if this whole, it should be like this, right? A given B, right, times B, right? It should be like this, but this is gone, so this, yeah, there. Okay, and so this definition is easy, but how this connect to our real world, right? It's like, suppose I told a coin Roy die, okay, and these two things should be independent, right? I mean, if I tell you the coin is head, can you tell me the roll of the die? No, probably not, right? If I toss the first time, okay, and maybe I toss another coin, right? The same coin may be related, right? But I have two coins. I toss one and toss the other, right? I tell the first one head. Does it tell you the other one? Probably not, right? Maybe the same coin, maybe you would think they're related, but the different coins, then usually it's not, right? So that would be the idea, right? Or is that clear what it is? Okay. And you may ask, why we need that? Okay. And we need that is because when we do the second half of our course, we talk about data. We assume when we collect data, each observation is independent. Okay. If I talk to woman number one, okay, I pick up the first observation is woman number one. Okay, I pick up this particular person, doesn't affect whether I will pick a woman number two or a man number one there. If whom I pick in the first observation affect what my pick in the next one, then observations are related. In that sense, your observations are not very meaningful, right? Because they are all the same, right? Or related, right? So that's why we do sample, right? I would not ask a family at the same time, right? Because if I ask his father, ask his mother, his son, his brother, and sisters, then they all very close to each other and they may be very similar. In that case, your observation is not a useful as much as if I have two independent observation. So this later we call random sample is by assuming that they're independent. Okay, so just like imagine if I draw a ball from a urn, right? I can't look at it, right? Then how can you guess? Suppose I have an urn of a box, right, with black ball and white ball, okay? And then I can't see what is inside, but I can draw balls from there, right? How can I guess how many black and white there? Okay. The best thing is you draw one ball there and put it back and draw again and put it back. Each draw is independent, right? The same observation. But if I draw, I don't put it back, then it's very difficult, right? Much more difficult than the other way around, right? So because every time I have the same study of the same boat, right? If I draw it, sometimes put it back, sometimes I don't, then I don't really know, right? Imagine this case, right? I have a box of ball there. I draw a ball there, and sometimes I put it back, sometimes I don't put it back, right? Right? Because someone want to mess up with me, right? Someone it gets put it back, sometimes I don't, right? I don't know whether they put it back or not. Then I have hard time to guess what's going on, right? So that's why we would assume independence there. I mean, the screen just shut down, so I can't see. But anyway, okay. So that is the idea, okay. And this example is like this. Usually, you want to check whether they are independent or not. Is to multiply them, right? Multiply them, then turn out that it's not the same as the intercept, then it's not independent. If the same is yes. This way to check. Right? Either you can check one of the three, and you can prove that three of them the same. Okay, because this is from the multiplication rule. Okay. And as I said, independence is talking about sampling with replacement. And that is something we assume because each drawn is independent. And that means that the larger the sample is more useful. Okay. So that is something that we assume. That's why it's important. And second, that related to our mutually exclusive idea. Okay. Just give you guys the idea what is independent. So if A and B are mutually exclusive, they are not independent. Why? Mutual exclusive means what? If one is true, the other one will be false, right? If other one is false, of course, can't tell me it's true or not, but at least they are not independent, right? Telling you something means something, right? So that's why I have a very funny pun, right? Independence and mutual exclusive or mutual exclusive, right? So if this is true, this must be false. If this is true, this is false. And similarly, you will ask, exhaustive is also not independent, right? Because exhaustive means if one is false, the other one must be true, right? So I tell you one thing, the other we know, right? Of course, I tell you A is true doesn't tell you B is true. I don't know, but at least I tell you one is false, the other one must be true. So independence and exhaustive is also mutually exclusive. Okay. Is that okay? But of course, this is technical, so you can forget about my pun. But that is the idea that what independence means, and we assume independence when we draw samples. Okay? Is that okay? So although we don't have time for a break, but I mean, I will still give a break, I guess. But very quickly, I talk about this and the break. So we are still on time. So I'm sorry I speak a little bit fast in the first half of our class, but I will resume the normal speed. I'm so sorry about that. Base rule. So this is, I guess, the single most important thing for the first half of our course. Okay, second half of course, I think is regression, but this first half, most important base rule, because the base rule tells us how you should update our belief is what we call the learning or human learning, what humans should learn, and this is what underline the also the machine learning. This how machine learn as well, and this is one of, if you learn machine learning class, this is one of the way that how machine would learn. And what is here, you can see we have an event A, okay? We have a prior, which means that initially what we think how A is likely to happen, okay? And very often what we learn is like we have some new information arrive, okay, which is B, okay? The question is, now we have no B happen, so we look at when we assess A after B had happened, right? Just remember the case of rolling a die. I roll a die, I tell you it's large number, right? Then you know that even is more likely than odd, right? Before you would think even is 1/2, right? Remember the example. Begin, right? Even is 2, 4, and 6 is equally likely, right? But if I told you it's a large number, then you understand that even is more likely because you have 2 even number out of 3 large number there, right? So if you learn, someone tell you, okay, we're doing roll a number, and someone is cheating, I tell you the answer, okay, this must be large, right? Give them some hint. Then you have update already, okay? The same as typhoon, right? We know now the typhoon number 1 now is now I think the typhoon is somewhere in Philippines, right? And after a few days, sorry, after a few hours, depends on how it move, right? You understand what's going on, you upgrade it to typhoon number 3 or A, or it go down, it disappear, right? So this is what it happened, right? New information helps us update, okay? The formula is not something crazy. The formula is like this. After this slide, I'll have break, okay? So we have this, A is here, and at the end, we want to go to this one, right? So from this one to this one. And how do you adjust? It's multiplied by this guy. Okay. And if you learn the terminology, I mean, this is a prior, right? This is a prior. And this is posterior. Okay. And if you look at the next slide, they will tell you this is the marginal. Okay. Marginal is what? How likely that this evidence comes out. And this is called likelihood. Okay, actually, this is in your next slide. And likelihood is given your initial what you think, how likely you get the evidence. Okay, and this ratio is how you adjust your initial belief. Okay, this red thing can be more than 1, can be less than 1, right? Suppose this more than 1, it's likely to go up, right? If less than 1, it will go down. Remember, this all positive number, right? So it must be less than 1. It's from 0 to infinity, right? So it go up, right? If the likelihood is higher than marginal, then it go up. If likelihood is less than marginal, go down, right? So it's just like given what you believe, is it likely to have, is likely to see the thing, right? Suppose the simplest thing you can imagine, if whether I tell you whether the A happened, right, doesn't sync to B, right? Then it cancel out. It's a 1. So it doesn't help you anything, right? Because it doesn't really tell you A and B independent, right? They were independence. If A and B independent, right? This is the likelihood of the marginal, the same thing. So it doesn't help anything. It's independent, cannot help. But if not independent, right? These two will be different. When they're different, we learn something, right? When we know B happened, we learn something new. Then you can go up and go down. And this is important because this is how you make business decisions, right? You learn something new, I want to change or not, right? That is underlying all the investment idea, right? Look at the stock price movement. Say in technical analysis, to see the price going up, right? Maybe a good signal to buy, right? The same idea here. And later you will see after break, sorry, just 5-minute break. Then we will talk about medical tests, right? This is the most important thing is if you have a medical screening, if you're positive result or negative result, how likely we conclude you have disease or not. So that's important because we need to see how good is the test, and you need to see how many tests we needed to ensure that what we want is accurate. Okay, you to make the decision there. So it's very important. Actually, this is very important for medical school. I mean, they will have to take this particular thing to understand how to administer more tests there. Okay, so let's a break of 5 minutes. I'm sorry for the short break because of my mistake, but I will still give the you reply in case you want to do it. But let's a break of 5 minutes because I know you need some toilet break or what. Okay, we're then here in case you want to leave any message there because I'm sorry, I'm slightly faster than usual, but hopefully. So in case you want to fill in, then please feel free to do so. Sorry. Let's resume 5 minutes late. So I mean, sorry for the short break. So I just look at this again. So that's good. No one have anything to say. Just make sure that some of you think it's Monday or Friday. So it's not. It's Thursday today. The weather. Oh, surprisingly, people said some people cloud. Well, almost equal numbers say Sunday and cloudy. So must be some cloudy there. I don't know because I'm inside, so I can't see anything. I'm just like in the prison for the whole day. Whatever. So this is independence, okay, and patience. Yes. Oh, I'm sorry about that. Thank you for your patience. Uh, I'm very embarrassed about that because usually I have a good memory, but to know what to when. But now I have to set up the alarm clock, make sure that I don't miss it. And I always told my son that he forget about the time, but now I just, oh no. I mean, this is truly embarrassing for my case, but okay. I mean, although I speed up a little bit, but I think it's so far it's okay. Yeah, I also skip my lunch. Indeed, I don't eat lunch. Almost don't eat lunch every day, so I always skip my lunch. That is because in Singapore it's so hot. I just skip lunch. So now I just have some chocolate at my room. So I just eat something. So if you ever drop by my office hour, then feel free to take some chocolate from my room. And maybe next time I can bring some to apologize. Maybe I should next time I bring some. This is my mistake. So I should be able to compensate somehow. But anyway, so go back to this. Oh, by the way, yeah. So let's continue this guy. Okay. Just to remind you before the break is we start from this one and we end up with this one with new information about the B. Okay. And do remind you that the adjustment is based on the comparison of the likelihood over the marginal. Okay. Is given the A, is it B getting more likely and less likely? Right? If telling you that no different, then you should be safe. Okay, so that is the idea. And you may first ask why this formula holds, but this formula is very simple because the numerator is just probability A and B, right? Because this is multiplication rule set. But if you look at this is exactly what we mean by conditional probability. So there's nothing new. Nothing new there. The zero new thing in this equation, right? Or you multiply this to the other side, multiply this to the other side, okay? And this is multiply this number to the other side, and this is exactly this equation. Look at this again. Look at this again. Look at this equation. You take B to the bottom, right? So that's base rule. So there's nothing deep in anything in terms of math, right? Just playing around with the symbols. Okay, of course, the deep part is not the simple thing why it's true, but how to use it, and this is something give us a very interesting thing. Okay. Let me first give you the idea why this is true in the tree diagram first, and then give example, and then give application. Okay, I hope that would convince you this is right. Okay. The first is this is our prior. Okay, is initially without an evidence. We have only know A is likely by PA, and not A happen is PA AC, and up to 1, right? This is something we know. That's without any information. That is this. Okay. And now we tell you B had happened. Okay. B happened. Then we look at our analysis. Okay. Analysis. Look at this. So suppose A is true. Then we see whether B had happened and B had not happened, how likely it's going to be. Okay. And do the same. Suppose A is not true, how likely you can see B? You don't see B. Okay. This is scenario analysis, right? You ask me how like A is going to happen. Look at, okay, if A is true, whether you have B or not. And if A is not true, whether B had happened or not. Okay. And multiplication rule tells us how you calculate these two numbers. Is going back by multiplying the edges, right? So you get this number there. Now remember, first is B had happened. So sample space is shrink, no longer this 4 outcome. Before, if I don't tell you anything, the sample space have 4 possible outcome. But now I have told you that B had happened. Now no longer you have these two guys. Only left these two. Okay. So you are saying that how likely A will be true? So it's just this over the sum of these two, because only these two branches open. It's proportional to this these two, sum of number. That's it. That's base rule, right? So if you call this A, I know this is called X, this is called Y. The base rule tells you this is X over X plus Y. That's it. That's base rule, right? Because the sample space is just X at X plus Y, right? And it only related to A is relevant. It's X. X over X plus Y. That's it. No more, no less. Exactly the space rule. Okay? Graphical is like this. Now give the example. Is that okay? So this is the example. I think I taught this for 10 years. I think now I'm getting more clear how to teach, because it's very difficult to teach. But now I think after 10 years of teaching of the same thing, now I think I so experienced that I think I can explain this in a much clearer way. I mean, so here we have bad A and bad B. Same question. 4 white, 1 green, and 1 white, 1 green. Okay. Again, you close your eye and draw a bad there. And then you draw a ball from the bad. Okay. Fair enough. So the question is, if I draw the white ball, how likely that is it going to be A or from B? Okay. What's probably A, what will it be? Okay. So first, I'm not going to talk about the math first. Probably I would try to convince you why this is important. This question is important, right? Remember, A and B are what? Economy. The green and the white are stock price up or down. Okay? And why we want to what was the question asking? We have drawn a white is likely to be A or B. So the question is, suppose the stock price goes up. Is it going likely to be good economy or bad economy? So we are using the stock price to predict economy in the future, right? That is when you learn macroeconomics. If you remember the 1000 classes, we use the stock market performance to predict the market, right? And then you learn that it's a leading indicator. So the stock market actually moves 6 months faster than the real economy. Okay, that's what it gives, right? Stock price actually give us the idea there. Okay, so this basically, I see the stock price goes up. You can infer whether economy is going to be good or bad. Okay, so that is explanation to this. Okay, and you can also think about it for accounting, same as this. Okay, A and B, maybe this is the whether the client is A, maybe the truthful reporting, B is a false reporting, right? And white, maybe you get your evidence that fit what he report, and green will be just you figure out inconsistent, right? Then you look at, okay, you audit, you go to the site and count the inventory, actually meet what he said, how likely that his the reporting is good. Okay, so this apply to auditing, right? Also apply to say quality control, all those things. So this is very natural, right? You learn something new and update, right? So that is very simple question. Okay, so later I will talk about next example will be more clear, but I hope this convinces you that this is a very business-oriented question, although I frame it the ball and draw it bad, but that is very natural. Okay. So first, even without calculation, you know A is more likely because you think because in the bet B, white is equal likely, and in the bet A, white is more likely than green. So if you throw white, then it's more likely to form A than B. Okay, but how likely? Okay, first is A given B. Okay, so what we want to know from this question is I want to know this. Given is white, how likely is A? And B, how likely is white? Initially, we know that initially without any data, we're here, right? Now we want to know this, given white, how likely is A and B? Okay. Before, it's close to my eye and draw. Now, once we've drawn the white, then I want to guess actually whether it's A and B. Okay? And let's do it, okay? And as I said, I want to do that, okay? And remind yourself, what is this formula here? Use the base rule formula. It's like this. Probability A given white will be, the denominator will be the white. You're updating on A, so just A is here. And just swap this guy. That's the formula, right? But this is marginal over the likelihood over the marginal, right? So we need to, this one is known, which is 1/2, right? Initially, that's what we have, right? Because you're updating this 1/2. The second is based on our analysis, if A, how likely you get the white, we know already, because this is 4/5, right? Because bet A have 4 white and 1 green. So we're done. So what's left is only this guy. How likely that we have white? Okay. And white, we can decompose two things. White under bet A and white under bet B, right? So that is what we have, right? And that's, we can apply directly this guy, right? This is white under A, this is white under B. Okay. White under A will be, you get A times how likely you get, which is already, we have this in the numerator. But only difference is we have B. But once you have B, you have half likely you get a white. So just add up 2 bunches, you get this number, right? So you are done already because you have 3 number there, right? So that's already in the next slide here. Okay. And you can do the same for B, do the same. But you see add up must be 1 because you have whites either A or B, right? So you can't have, they are complement. Okay. Add up must be 1. But you can see from here, 8/13 is larger than 1/2, right? Right? Because this guy is bigger than 1. And this guy is less than 1. So if you draw it, if you draw a white, A from 1/2 up, go up by 8/13. If you draw then B will drop from 1/2 to 5/13. Okay, so that is how we learn. Okay, is that clear? Okay, of course, you may ask, can we do one more round, right? You draw the ball again. Suppose I drew the ball and draw a ball again, then you can keep doing this. Okay, but let me not use this example because this example is complicated. Let me use another example, and this example will be very good because I think this is the most applicable example. Is screening. It's medical screening problem, and actually that's what you do. Your doctor actually calculate in their head how to do it. Okay. So in consider case, I guess COVID is the thing in the past, but not so past ago. I mean, in your high school, you had the COVID. You still have. I don't know whether you still have the memory, but you will see in that time. I mean, you do a lot of COVID tests. Okay, why? You will see why now. So consider a case where we have a disease and 40% of population infected. Okay, and now we have an imperfect medical test. To be sure, actually, most of the medical tests are imperfect. They absolutely said no 100% correct one. Okay, and we just make the math easy, but you can also change the number. Everything holds as well. So medical test is imperfect means that if you are infected, 80% will say you are test positive. Okay, means 20% you can't figure out by single test. Okay, and also there's another thing is if you are uninfected, you have no disease, but it's still at 40% say you are positive. Okay, so it's not very accurate. Okay, but the number doesn't really matter. You can change the number to more realistic one, but the result is the same. But this is the idea. Okay, so let's A is the being infected and B is positive result. Okay, and because the population has 40% infected, this is our PIRA. Initially, 40% of people are infected. Okay, so we're going to do is the doctor, the government asks you to do a test. Okay, we want to know if positive result is there. Okay, how likely that you are infected. Okay, or the other way around, if I am given the negative result, how likely that you are actually infected. Okay, of course, or the other case round is I have negative result, how likely that you are okay, so you can go home, right? So this is very important, right? And this is initially what we have, right? And this are what we want to know, right? These are all we want to know, okay? And these are all things that posterior, right? Given that the evidence, we want to know what's going on. And these two are coming from our testing technology, right? 0.8 and 0.4, right? Why this 0.8? Here means given this guy is infected, you have 80%, you figure them out, right? And given this guy is not infected, you have 40% say they are positive. Okay, these are all the information. Okay, is that clear what we're doing? So what we do is we know in the population how likely that people get infected, but now we want to see. I give a screening test and see how likely that after the test, how we change our initial belief. Why I want to do that? Because suppose a COVID, right? I know it's 0.4 is high, so I want to see when I can get them out, right? Because that's what happened, right? I don't know where you are, but at the time 5 years ago, when you try to enter Hong Kong, right, you have to put in quarantine hotel, right? At that case, right, PA is very large, right? Because everywhere have disease, right? Then you have to make sure that the guy is okay, right? Put in quarantine hotel for 2 weeks, and then test 3 or 4 times negative before he can get out of the hotel, right? So that is what happened. And then why you need 4 or 4 times? You will see very soon. Because of the test is not very accurate. Then you have to test many times until it's safe. And also, right, if you're in the hotel, right, when you have a positive test, they don't immediately put you into the hospital, right? You will do multiple times before they take you to hospital as well. The same idea here. Okay. Unless the PA is very high or very low, you don't really send people to home or send people to the hospital. You keep them in the hotel. Okay. But anyway, let's do the calculation. I will tell you more. Okay. So let me okay, calculate. Okay. First, remember what we go is this guy, right? Initially, we have probability A. Okay. How likely people get infected is 0.4, right? This is the thing that initially we want to have this guy. Okay. And first is the base rule is like this, right? This is the base rule. Let's apply. And this guy is 0.4, right? So we need to get these likelihood and marginal. Okay. So how did we do that? First, we calculate whatever we can calculate first. Let's send it in the math problem. I think this is how your high school teacher teach you, right? If you're given all the information there, you try to calculate whatever you can calculate, and before again you can try to do things, right? I don't know how your math teacher teach you, but this is how I teach the high school kid, right? When I teach them, okay, whatever the information given the question, you just calculate whatever you calculate, collect all the information, and then before you proceed to the next step, okay? So that's what I do. I know 40% of people have disease, means that 60% of people have no disease, right? That's the first thing I know. Okay. The second thing I want to know is, okay, look at this Bayes theorem. This is given you have disease, how likely that positive result, actually we know already is 0.8 because this is the testing technology, right? So again, what we need is the denominator, this guy. Again, right? It's always, the numerator always know already. It's actually the denominator, the marginal, the probability evidence is something I know. Okay. How likely we have positive result? Is positive result under you have the disease and positive result you don't have disease, right? This is total probability. Okay. And you decompose it into two parts. And then under that is like you do the multiplication rule again. Is under you have disease, how likely you have positive result, and you don't have disease, how likely you have positive result. Okay. And this is 0.4 times 0.8. This is 0.6 times 0.4, which we know already, all the numbers. Then we're done. We put it there. You got 57%. So from 0.4 to 57, right? So each time this y, this is more than 1, right? Because you would likely to see the evidence under A, right? So under you have the disease, you're more likely to see positive result, right? So that's why this is more than 1. That's how you adjust. And probably you ask the next question. Now we know this question, right? I think it's good to look at the diagram here, right? So remember that you want to know initially this is what you know. Okay. Now you send the guy to the lab and have a positive test result come back. Okay. And to ask how likely actually he's infected. Okay. So what you do is you look at these two outcomes, which is positive result, which is new sample space. Suppose this is called X and Y. What we want to do is X over X plus Y, right? Because X plus Y is the total new sample space. And X is only relevant to what we want to know, right? Because X and Y are possible. And we know whether we want to know whether he's infected. So it's X over X plus Y. And how you get X is you go back, multiply these two numbers, right? And Y would be, you multiply these two numbers, right? And these numbers are known, but don't worry. These two are complement. If this is 0.4, this is 0.6. Right? So this, you multiply these two over these two multiply plus these two multiply. And that's it. This is the base rule. Is that clear? Is that okay? Now, we want to know the other case is if it's negative test, how likely he still have the disease, right? This is want to see whether it's sufficient for us to send him home, right? Negative test is still high enough. It's too high, then I don't want to send him back, right? Before it's 0.4, if negative result is rise downward, right? It cannot be more than 0.4, right? So how do we do that? But you just go back to this one without going to the calculation. Now, we want to know now it's no longer this guy, right? We know it's going to be this guy method now, right? So we want to know this, right? Suppose now this is called x and y now, right? It's still x over x plus y, right? And we need to figure out what this number is, right? This is 0.2 because add up must be 1. And this error must be 1.6, right? And this is 0.6. So what we do is x will be 0.4 times 0.2, y will be times 0.6 times 0.6, right? So this x over x plus y. So this will be the solution we will see here. Okay, so we figure out this is the base rule, right? And this is x plus y, right? Okay, and then you just figure out this guy is x, right? So that is how you get that. And remember, you start from 0.4. Look at the equation. You start from 0.4, you become 0.2, right? Why? Because this guy is like 1/2, right? So we just from 0.4 drop to 0.2, more or less, right? Half. So let's summarize what we have seen. So initially we have 0.4. A positive result gives us 0.57, right? So it go up by 1.4, right? Or 40% if you learn to say, right? Up by 40%, right? And if negative result, you drop by 50%, more or less, right? Approximately. So although we don't do it, but you can easily see this question. If I ask the guy to do a test again, how can we apply the base rule, right? Because we learn machine learning, right? So we want to learn if we know that the first test result is, say, positive, say, okay? What happened? You send him to the lab again, come back positive. What is the result? What do you think? Very simple. If the first result is positive, okay, it's this one. Your pyra no longer 0.4. Your pyra now become this posterior become your new pyra. That become 0.56, 0.57. Okay. And you come back, you positive result, then you go up by 40% more. Right? Because the test doesn't change. Okay. If you come back negative next time, then reduce by half, become 29 or 130%. Right? So a positive and negative doesn't go back to 0.4, right? Initially 0.4. If you're positive, you jump to 0.57, but negative, you become 0.3, drop more than initially. Okay? And if you have one negative, become 0.2, 20%, right? If you have another negative, then it become 10%, right? Because each negative will reduce by half, right? Another one become 5%, and the other one become 2%, 2.5, right? Or something like that, right? So that is how you can update multiple times. Okay, of course, in our class, I don't require to do multiple times. I think I don't, but at least in the maybe in assignment, but it's not exam. Or we only I ask you to do once and not twice. But you can see how you can apply repeatedly, right? Because the prior is what? Nothing, but just what given evidence. So you can be up, down, up, down, up, down. Yes, no, yes, no, yes, no, yes, no, right? So that's why doctor can ask you to do many times, right? Because the first time say, maybe yes. Oh, next time say no. The first time say yes. The second time no, right? That's what happened, right? It happened when you go to dating, right? So suppose you see the other man and woman, sorry, boy and girl, right? Very attractive. Immediately you jump, right? From point 4 to 1, then get married, done, right? First love at the first sight, done, right? And sometimes not, right? And people now get in a relationship for a very long time, right? So why? Because you have good signal and bad signal, good signal and bad signal, right? You see the other boy or girl, maybe he's rich, but his behavior is not very well, and then he seems to be nice, but sometimes he didn't reply to my message, and sometimes he's good. He remember birthday, but he's not good to me, and then so on and so forth. You keep update, right? Happens, right? And sometimes you have date for once and then forget for the rest of the life. Happen, right? Depends how you update the thing. That happen with information updating. So it takes time to go up and down. Okay. So I hope I convince you that this is how machine learn, right? Because keep updating information he learn, right? And sometimes learning can be good, sometimes bad, but it takes some time, right? But I have convinced you why in the COVID time, right? People tend to stay in hotel for a long time because of the test of the COVID is not very accurate, right? If we have a very accurate thing, you just know people can need to stay for 2 weeks, right? So that is one of the reason. So although I don't have enough time, same as other class, so we are not fall behind. So the next class, we'll talk about some counting thing, telling you all this thing, and then a few slides, then we're done for this chapter. Okay? So although I'm sorry for today, a little bit late, but I cut our break short, so everything is all right. But as I'm late, so I stay around to answer any question you may have. But I'll see you next week. Have a nice weekend.